Hello everyone, my name is Pratik and I'm going to present my project work, which is on Manifold Learning Algorithms and the relationship with Kernel Principal Component Analysis. So the problem statement is to do nonlinear dimensionality reduction on datasets which are actually embedded in a manifold fashion. We also need to test and understand why the problem is so complex. And then finally, I would like to outline how these methods are directly related to kernel methods. First, we would like to know what is a manifold. Manifold is actually data present in a very high dimensional space, which actually has a geometric structure which can be embedded into a low dimensional space, just like the example Swiss roll. As can be seen here, it is actually a two-dimensional surface or a plane which is rolled into a three-dimensional space. So our objective is actually to flatten or unfold this Swiss roll. It can be intuitively seen that linear methods, linear classifiers or linear regressors cannot handle these kind of data. Even kernel version of dimensional reduction methods like principal component analysis, which is also known as KPCA, with Gaussian kernels or maybe polynomial kernels, fail to unfold these kind of data. As can be seen in this particular example, where we take an S-curve, which is again a manifold, and we sample some of the data points there. However, when we reduce the dimension to 2 using kernel PCA, we really cannot see the underlying structure. That's why we need specific manifold learning algorithms. The first algorithm is isometric feature mapping, which is also known as isomap. It's a global idea. What we do here is we actually design a graph which contains the geodesic distances between each data point. It is estimated using piecewise Euclidean distances between the neighbors. And then on this graph we perform a classical multidimensional scaling so that we can preserve the distances as much as possible when we translate this dataset into its low dimensional representation. Next, another algorithm, which is known as Laplacian eigenmap, is based on computing the Laplacian matrix out of an adjacency matrix. Now, what is an adjacency matrix? It is composed of the similarity values between two data points. It might be unweighted or might be weighted. Then we find out the generalized eigenvectors corresponding to the smallest d eigenvalues of the Laplacian matrix, and these d eigenvectors form the new feature space, which is actually d-dimensionals only, a reduced form. The next algorithm is local linear embedding. It is shortly known as LLE. It has a totally different intuition. The idea is to consider each data point to be a linear combination of its neighbors, and the optimal weight matrix is calculated. Let's say it is W. Out of this W, we compute another matrix called M, as can be seen in this equation, and then we find out the smallest d eigenvectors, ignoring the last one, which is corresponding to the eigenvalue 0. It is just a uniform vector, so we just ignore that one, and then the next d eigenvectors, the smallest ones of the matrix M, give the low dimensional embedding of the data set. Now we briefly discuss what is kernel PCA. As you may recall, it uses a kernel function, which are normally Mercer kernels, to form the kernel matrix or the gram matrix. Then the matrix is centered, and then we perform an eigendecomposition of the matrix, just like PCA. And then we get back the transform data, which is having a low dimensional space, which is embedded in a low dimensional space. Now All the manifold learning algorithms which we just discussed can actually be represented as spatial forms of kernel PCA. As you can see in isomap, the kernel matrix looks like a centered form of the matrix D, where D is the squared geodesic distance matrix. It contains all the squared values of the geodesic distances between each points. Similarly, in LLE, we can subtract the matrix M from lambda max times I, where lambda max is actually the maximum eigenvalue of the matrix M, and then perform a kernel PCA on this KLLE matrix. It will give exactly the same results. In Laplacian eigenmaps, the kernel matrix is nothing but the pseudo inverse of the Laplacian matrix itself. Now we see some of the examples. Let's say Swiss roll, the data set we discussed in the first. If we perform isomap on it, it can clearly be unrolled. As you can see, the blue portion, the green portion, and the yellow and the red, they actually follow the same order as is in the three-dimensional space in the original data. However, Laplacian eigenmap doesn't quite give the actual underlying structure. LLE tries, it gives quite an approximate solution, but is not as good as isomap. The reason why isomap works so well is because it computes the geodesic distances between each point, and then it performs the spectral decomposition. Now we take another example, which is the S-curve, and almost all three algorithms worked fairly well. Not Laplacian eigenmaps, but still it is okay. I mean, if our problem would have been clustering or classification, then we could have used a linear classifier on this Laplacian eigenmaps output too. Now we want to see how these algorithms work when the data is sparse. Let us take a sphere data, which is having a punctured hole on its top, and the lower data are sparsely sampled and the top portions are densely sampled. As you can see, isomap totally fails here. However, Laplacian eigenmaps and LLE, they give pretty good results. So we can conclude that even if isomap is slow, but still it is effective. It is slow because we try to compute the geodesic distances using different Euclidean distances between each neighbors, and then out of this matrix, which is not at all sparse, it's quite a fully connected matrix, we perform the spectral decomposition. However, LLE and Laplacian, they work on quite sparse matrices. I mean, if we choose the neighborhood parameter k to be very small, then they are quite sparse matrices, and that's why they can handle sparse data well also. However, these algorithms are very sensitive to the parameter k. If we take it too less or too big, the manifold learning won't quite work good. We just showed how all these three algorithms can be explained as spatial versions of kernel PCA. And thus, it also gives us a direction for research that any modulations which can be applied on kernel PCA can also be applied analogously to these manifold learning algorithms too. Okay, that's all I have to say for my course project. Thanks for listening. Thank you.